If we want any chance at meeting our 2030 climate goals, 80% powered by renewable electricity and 5 gigawatts of that coming from offshore wind, we need to get our act together. Building the infrastructure is only half the challenge. Maintaining it is the real one. Subsea cables stretch for tens of kilometers across the seabed. Currently, inspection models for these cables rely heavily on manned vessels and remotely operated vehicles. Guess what? This is not a scalable model.
So why, in the 21st century, are we still sending people to do this? Can't we do better? We think so. Initially, we started off with divers, then went and inspected the cables themselves. But we progressed, and now we had ROVs, which are the currently deployed tech. But now the cutting edge is AUVs, which is the next logical step. But in all these cases, what do we need to measure?
Thanks for that, Joe. Underwater cable inspection is like working in the dark, so the obvious solution is to light it up. The vehicle needs to be able to collect data and send it back to technicians onshore to process and diagnose. To do this, a typical sensor toolkit attached to our autonomous vehicle would be side scan sonar to give a continuous acoustic image to spot exposed cable, foreign objects. If the visibility is bad, imaging sonar confirms close range details, and smile. It's cameras, of course, because engineers love a simple, I can see it, I know it works, sanity check. To monitor the seabed shape, we use a multi-beam, which builds a high-resolution 3D bathymetry, so we can quantify scour, erosion, and settlement. To monitor the burial depth, we can use a sub-bottom profiler, which shows the trench and the sediment layers. And to follow alongside the cable, we can use a magnetometer, which double checks alignment and flags any ferrous hazards when surface visibility is low. To answer any stakeholder questions, we can use a hydrophone to detect noise and manage any biological impact of the cables. To do this, there are two orientations, the first being a tethered orientation or a wired orientation. This receives surface power from a vessel on the surface and real-time fiber optic data from the vessel underwater. This is great for slow-up inspection, however the tether adds drag and poses snag risk, and it does suffer from the same sort of consequences of environmental hazards as the current solution using a boat. Which is why we believe that the better solution is using a cordless or an untethered vehicle. It is both efficient for long corridor surveys, it doesn't have any drag, and although its endurance is slightly limited due to the fact that it is running off of a battery, we believe that it is enough for the mission needs of a provider like EirGrid.
To provide an accurate cost estimation for implementing the proposed autonomous system, we began by researching the market for subsea inspections. There are several industry leaders in this field based in Ireland, such as Ocean, who operate USVs globally, or Ireland's National Maritime Institute, who operate state-of-the-art ROVs equipped with complex sensors. There are also many more well-established companies. We compiled a table with the available data on cost and technical capabilities of these vehicles to better understand the survey methods and their differences. Seen that the quality of data the AUVs can obtain is far superior compared to base model ROVs. Applying this information to the Tunnua site helps to realise the financial gains of autonomy for EirGrid. Tunnua, Ireland's next offshore wind farm, covers an area of over 300 kilometres squared, with an average depth of about 60 metres. Based on our data, we estimate over 150 kilometres of undersea cable will be required to support the project, for which EirGrid will be responsible to maintain. Given the inspection methods for a single survey of the expected cable infrastructure, AUVs stand out as superior in survey time and cost, not to mention the higher frequency of inspections possible and more diverse data collection.
Now, we can't talk about innovative ideas without talking about some of the challenges, and legalities is one of them. And it can get quite boring sometimes. So, we got Jack to explain this for us. Jack, can you make this interesting?
Indeed I can, Joe. EirGrid's critical path to getting these AUVs in the water comes down to regulatory compliance. First, the legal framework. The old Offshore licenses are gone. Under the MAP Act of 2021, AUV operations are classified as a maritime usage. EirGrid's top priority is securing a specific maritime usage license from MARA. Second, environment and heritage constraints. Because the Irish seabed holds many historic shipwrecks, a strict discovery protocol is required if anomalies are found. EirGrid must also mandate appropriate assessment screenings to prove the AUV's high-frequency sonar won't disturb protected marine mammals in special areas of conservation. Operational liability. To comply with international collision laws, unmanned vessels must broadcast AIS signals to avoid other ships, and for GDPR compliance, subcontractors must use privacy by design software. This automatically blurs boat registrations and faces before footage ever enters EirGrid's database. There are some legal challenges to navigate through, but there is a clear pathway. Hope that helps, Joe.
Thanks, Jack. Now, safety is also a concern. Moaz has been looking into this.
Thanks, Joe. Well, underwater cable inspection today, it's not the safest job in the world, and as you can tell from this very professional headline, we're talking about safety. You got boats, which are limited by weather. You got rough seas, which will have you way behind schedule. And I know she looks happy with that clock that's ticking down, but you won't be. Why? You have deadlines. Now, imagine, alongside all of that, you need divers making it harder again. You got depth limits, time limits, current, low visibility, and then permits that are thicker than his wetsuit. Solution? Cute robots. Nah, play. Real solution is we shift the campaign towards unmanned inspection drones. Fewer offshore days, fewer launches, and fewer humans standing near suspended loads. And with the risk-based inspections done more regularly, issues get caught way earlier in all conditions. Safer coverage, better data.
Okay, so we covered the human factor, but what about Mother Nature?
Mother Nature, the giver of life and beauty in our lives. It is the goal of all humans on Earth to protect and maintain Earth's beautiful bounty. Of course, this is a common goal shared by EirGrid. According to their grid implementation plan from 2023 to 2028, it is EirGrid's policy to uphold best environmental practice in design and appraisal of onshore-offshore grid development. EirGrid places such an importance on the environmental and heritage protection that their 2024 stakeholder engagement report reads that EirGrid's major stakeholders are major environmental protection agencies such as OCEAN and CIEEM.
To find out more about Ireland's diverse offshore ecosystem, and to Seahorse Aquatic Specialists to interview Alex Bendorf, marine expert.
So what is the importance of biodiversity off the south coast of Ireland?
Well, Ireland is actually a biodiversity hotspot because of the Atlantic current brings in phytoplankton to the shallow seas around Ireland's south coast. So these are special areas of conservation for a number of species that use this as a breeding ground to raise young and fry.
Roughly how many fish are endangered?
So the ocean in total is home to about 1,500 species of endangered animals. In Ireland, the most notable species would be basking sharks, fin whales, and bottlenose dolphins as well.
And are any of these in particular susceptible to drones or human intervention?
Yeah, absolutely. So any fish that uses electroreception, so elasmobranchs, which are sharks, rays, and skates, they use electric currents in the water to find prey. So they would be affected definitely. And then also migratory species such as salmon and trout, they need to find their way back to their breeding grounds upstream. so they would also be affected by sonar and EMF. Interesting.
Thank you, sir.
No worries.
The Tonua area where EirGrid plans to develop their 2 substations is an area of interest for fair seas and their special areas of conservation. EirGrid needs to be extra vigilant when developing in these areas. This is where our drones come into play. Autonomous submersibles can scour the seafloor for marine life and keep a constant log of marine population density and track migration data. From this, we can develop an algorithm that can predict migration patterns and reduce wind farm activity, helping bolster a healthy ecosystem where both humans and fish can coexist.
Now, you might say this is great and all, but it's just fantasy. Well, Jack's back to tell you how it's done.
EirGrid isn't going to buy and operate a fleet of robotic submarines in-house. Instead, they will be subcontracted out to specialised marine survey companies. Here is the 5-year plan to get these robots in the water and establish a fully predictive maintenance ecosystem. Before a single AUV gets its fins wet, we have a 12 to 24 month regulatory runway. Our subcontractors need MARA licenses and environmental green lights from stakeholders and government bodies. EirGrid will also lock down strict data protocols so that when an AUV scans the seabed, that data instantly feeds into the live database. Once the paperwork is signed, the rollout begins. EirGrid won't just blindly trust the robots on day one. On the East Coast assets, EirGrid will run a hybrid model in the first year. AUVs will launch from the same ships as traditional ROVs. The AUV's high-speed sonar will be compared against the ROV's live camera feed just to make sure they are seeing things clearly. As EirGrid builds the new South Coast infrastructure in Tonua, AUVs will inspect the newly laid cables. Subcontractors will start using machine learning to automatically flag exposed cables or damaged rock. Year 3 is where EirGrid drastically cuts its operational expenditure and carbon footprint. The company will stop using large, crewed ships for routine patrols. Instead, AUVs will be launched from uncrewed surface vehicles. The subcontractors will monitor the fleets from an onshore command center, and EirGrid will only send out a human crew if a robot flags a critical fault. Finally, in year 4 of operation, across all its offshore assets, EirGrid will shift to a pure autonomous model. The continuous stream of AUV data will automatically update the digital twin, predict where, and tell EirGrid when to dispatch a repair crew before something fails. In just 5 years, EirGrid can transition from reactive, carbon-heavy inspections to an autonomous, low-emission network.
As Ireland accelerates offshore wind development, the infrastructure beneath the surface becomes just as important as the turbine above it. Our analysis shows that integrating autonomous underwater vehicles into EirGrid's offshore asset strategy is not simply an operational upgrade, it is a strategic transformation. By replacing reactive inspection cycles with continuous, data-driven monitoring, AUVs reduce operational risk, remove personnel from hazardous marine environments, and significantly lower long-term maintenance costs. More importantly, they enable something far more powerful: intelligent asset management. Through predictive maintenance, digital twin modeling, and optimized inspection scheduling, EirGrid can move from responding to failures to preventing them, extending asset lifetimes, reducing unplanned outages, and strengthening regulation compliance. But this shift is not only technical, it is environmental. Autonomous inspection is inherently less intrusive than traditional manned marine operations. Reduced vessel traffic means that lower emissions, lower noise pollution, and minimal disruption to sensitive marine habitats. The Tonua development provides an ideal proving ground, a project located within a sensitive marine environment where grid reliability and biodiversity protection must coexist.
If Ireland is to deliver offshore wind that is safe, sustainable and scalable, then autonomy is the way forward. Cleaner grids require cleaner solutions.